You're live, so I don't want to delete that or whatever you want to do. Apologies for that.
Okay, no worries. Okay. All right, so this is take 3. This is the chemistry paper 2 for AS level, and from summer, May, June 2013. It's the structured paper. Good, all right, so they give you easy question to start with. Sodium hydroxide, hydrochloric acid, base and acid makes a salt and water. That's GCSE knowledge. So NaOH plus HCl. That's going to make a salt and water. Easy one to start with. Next one, you've got an ammonium salt and sodium hydroxide. You know that with ammonium salts, when you warm them with sodium hydroxide, you always release ammonia gas. So that's going to be happening over there. Here's the ammonium salt, ammonium sulfate. We're reacting that with sodium hydroxide, a strong base. We're going to be making ammonia gas from ammonium salt. There's 2 ammonium ions. We'll get 2 ammonia molecules of gas. The salt we're making over here is sodium sulfate. And to balance everything up, we need some water. Balance that up there, and balance that up there. Good, those are the equations we're going to be working with. Okay, again, giving you easy things to start with here. You have to remember, of course, that concentrations are amount in moles divided by volume. You can tell that by looking at the units there. So in this case, we want to know the amount, the number of moles. You just rearrange so that the amount is the subject to the equation. The amount is concentration times volume. You need to plug the numbers in there. Concentration was 2 moles per decimeter cubed, isn't it? And the volume was 39.2. Now that's in centimeters cubed. We've got to convert that to decimeters cubed. You divide by 1,000, multiply that up all together, and you end up with 0.0784 moles. Easy calculation to start you off. Okay, carrying on. You've got another concentration calculation to do here. You have to look back at the question, and this time you're calculating the amount, and your concentration again is 2.0 moles per decimeter cubed, but your volume was 29.5 centimeters cubed. Convert that to decimeters cubed, divided by 1,000, multiply all that up, and you get 0.059 moles. Okay, good. Now, you've got to use those 2 answers to calculate the amount of sodium hydroxide that reacted. You're just going to find the difference between those 2. So the difference between those 2 ends up as 0.0194 units again, moles. Very good. Now, you need to, at the next step, you've got to go from the amount of sodium hydroxide that we calculated there to the amount of ammonium sulfate. And if you look back to the equation where you worked out the stoichiometry is 2 moles of sodium hydroxide for each mole of ammonium sulfate. So you've got a stoichiometry here of, let's get the pen in range. You've got a stoichiometry of one of those, to two of those, to sodium hydroxide. All right, now you just calculated the amount just up here, 0.0194. So get the penning range again, 0.0194 moles. And so the amount of ammonium sulfate is half of that, because sodium hydroxide is twice the amount of ammonium sulfate. So half of that is, it's easier in scientific notation now, 9.7 times 10 to the minus 3 moles. All right, so we've got the amount, and we've got to convert an amount that we just calculated there to a mass. So again, easy stuff really. You need to know that the amount is equal to the mass divided by the molar mass, just rearranged to make mass the subject to the equation. So mass is the amount times the molar mass. So we're trying to work out the mass there. The amount we know is 9.7 times 10 to the minus 3 moles. The molar mass is just the relative molecular mass in units of grams per mole. So we can work out the relative molecular mass here. We've got nitrogen. Now there's two of those. So each nitrogen is 14, so two of those gives us 28. Hydrogen, each of those has a relative atomic mass of 1. We've got 8 of those to get together. Sulfur has a relative atomic mass of 32.1. There's only 1 of those, so we just have that there. You've got oxygen, relative atomic mass of that is 16. We've got 4 of those. Add them all together, it's 64. Add them all up. You've got a relative molecular mass of 132.1. And to convert the relative molecular mass to the molar mass, you just multiply it up by the units. So you've got 132.1 grams per mole. Multiply those two together, and you get a mass of 1.284 grams of ammonium sulfate. Now, if you look back to the question at the beginning, it was actually, there was a mixture, wasn't there, of this ammonium sulfate and some sand, I think, if you look back at the question. So you've got to calculate the percentage by mass of ammonium sulfate. Now, the original sample, the mixture of sand and ammonium sulfate, had a mass of 2.96 grams. So that's the sample mass. And we've worked out how much of that mixture is actually ammonium sulfate. So the percentage mass in the sample is going to be, percentage by mass, is going to be the mass of ammonium sulfate that we had, which is 1.284 grams, divided by the total mass of the sample. That's all the ammonium sulfate and the sand. And we had a sample mass of 2.96. And of course, we want a percentage. We've got to multiply that up by 100 to give us a percentage. Work all that out, and it gives us 43, and then 2905 was what I got on my calculator. That's a percentage. Now it's saying, okay, you've got that value, but we need it to a suitable number of significant figures. Well, what is a suitable number? A suitable number of significant figures is you need to look back at the data that you had to do your calculations back in the question and give the answer to the smallest number of significant figures that you had in the question. Now, if you look back at the question, all the data there is to 3 significant figures. So we've got to give our answer here, percentage, to a similar level of precision, 3 significant figures. So just take that to 3 significant figures, that's 43.3%. And just be absolutely clear, I'll put in brackets here, 3 significant figures. That's our value there. Okay. So we've been doing some quantitative work, and now we've just got some descriptive work to do. Talking about the use of fertilizers. If too much of the fertilizers end up in rivers, you get this effect called eutrophication. Basically, that means that the aquatic plant life, algae and plants, overgrow. There's so much fertilizer that they grow much more than they should. There's an overgrowth. And so it's asking here, what are the processes that are going to occur when there's excessive amounts of nitrogen fertilizers? So it's giving us a clue there, isn't it? That it's looking for more than one process. It's asking for plural processes. And we've got 2 marks down here as well, haven't we? So we're looking for two points. And I would say the first is excessive or overgrowth of algae. Typically algae, you see this as a kind of bright green bloom, they call it, on the surface of the water, or aquatic plants. So that's the first process. And the second point is that when this huge amount of excessive overgrowth of algae or plants, when these organisms die, then the bacteria that consume the dead algae or the dead plants, they're working so fast, or they're growing so much, the bacteria that are consuming these dead plant materials, they use up all the oxygen that's present in water, dissolved in the water. And so you get an effect of, you call it hypoxia, that all the oxygen that would normally be dissolved in the water has been consumed by the bacteria, which themselves consuming the dead algae or the dead plants. So hypoxia, bacteria use up dissolved oxygen, decomposing dead algae. Okay, and other aquatic plants as well. So we get 2 marks there because we've listed 2 processes. One is the excessive or overgrowth of the bacteria, and then this state of hypoxia, when the bacteria that are consuming the dead plants and algae use up all the oxygen that's dissolved in the water. And that then causes a problem for other aquatic life, such as fish, which depend on the dissolved oxygen. Okay, still talking about ammonia here. So Haber process produces ammonia. Well, what are the other uses for ammonia apart from fertilizers? You need to know, well, ammonia can be used to make nitric acid, can be used in the making of explosives, and also the polymer nylon. So those are some other uses of ammonia from the Haber process. You could even need 1 mark there, so you just need to choose one of those. Nitric acid, explosives, nylon production. Good. Interesting. The second question is still keeping on about ammonia. Ammonium nitrate fertilizer is manufactured from ammonia, gives you some steps in the process here. You've got an equilibrium. You can see that all of these reactants are gases. And so this equilibrium expression is going to be expressed in terms of the partial pressures. So they want you to give a value for the equilibrium constant here, expressed in terms of partial pressures. And you do that by putting the lowercase p there to represent the partial pressure. And you start off with the products on the right-hand side of the equilibrium. So you've got the partial pressure of nitrogen dioxide and the partial pressure of the water. You can see the water is a gas because this reaction is being carried out at a temperature higher than the boiling point of water. And you just have to remember to add as an indice up here the stoichiometric coefficients that you see in the equation. So we'll have a 4 and a 6 as indices. And then the denominator is the reactants. You've got the partial pressure of ammonia, and you've got the partial pressure of oxygen. And again, we use the indices, which are based on the stoichiometric coefficients from the equation. All right, so, and it also tells you up here something about how they're measuring pressure in kilopascals. And so you want the units for this expression. Well, the units is just multiplying up in exactly the same way that the quantities are being multiplied up. So you've got pascals as your unit, and you've got pascals to the power 4 times pascals to the power 6, gives you pascals to the power 10. And the denominator of the equation, you've got pascals to the power 4 times pascals to the power 9. So you've got that. And so if you divide pascals to the power 10 divided by pascals to the power 9, you just end up with a unit for the equilibrium constant in pascals. Good. So classic questions coming up then on the effect on the equilibrium. And you've got a couple of points here. You can see you're asked to say what the effect on the equilibrium will be, and then you've got to explain your answer as well. And so we're just using Le Chatelier's principle here. Remember that for Le Chatelier, for a system at equilibrium, if that equilibrium is subject to a change, and our changes here are temperature and pressure, if a system at equilibrium is subjected to a change, then the system will move to minimize the effect of that change. So if we increase the temperature, the system will move to minimize that effect. Or if we increase or decrease the pressure, the system will move to minimize that effect. So we've got to first of all say what the effect is. Well, if we increase the temperature, just go and look back at the equation, you can see that it's written up there with an enthalpy change that's negative, which means the reaction is exothermic. So if we increase the temperature, the way the system can minimize that change is to absorb some of the heat energy that was introduced by raising the temperature. And it absorbs the extra energy that's been added by raising the temperature in an endothermic way, which is the reverse reaction of the reaction that's given up here. We've got to have an endothermic process. And so the position of equilibrium is going to move to the left-hand side. And so you should say more reactant is formed on the left-hand side. And the reason for that is that the reverse reaction is endothermic, because the forward reaction is exothermic. Okay, so we've got our 2 points there. And again, we've got to have an effect and an explanation. And this time we're increasing the pressure. And if you look back at the equation up here, well, we're decreasing the pressure, and so the system is going to move to minimize that change, and it can increase the pressure back by moving to the side of the equation where there are more molecules of gas, not less molecules of gas. And so we're going to have, on this occasion, as we apply a decrease in pressure, we're going to have more product is formed on the right-hand side. So we've got our effect, we've got to explain that, and we can say there are more molecules of gas on the right-hand side of the equation. So we've got our effect and our explanation, we've got our 2 points. Okay, still talking about this equilibrium, and it's talking about the standard enthalpy change of formation. Now you need to recall that the standard enthalpy change of formation relates to the formation of 1 mole of a particular compound. That's you need to remember we're working, when we're using these values here, that those values refer in that case to 1 mole of ammonia or 1 mole of water. So that's what those values are describing there. Okay, so we're coming here to an example of Hess's law, and if you remember, Hess's law basically says that you can have an enthalpy change, and it doesn't really matter what route you take as long as the starting conditions and the end conditions are the same. So you can have this route here, that's fine, or you could have another route. It doesn't really matter which route you take, whether it has one step or two steps, as long as the starting conditions and the ending conditions are the same, then the enthalpy change will be the same whether you take one step in one route or two steps in another route. And because we've got this prompt up here about enthalpy changes of formation, then that's giving us a pretty good clue that we've got to use an enthalpy of formation in forming a different route to help us do the calculation here. So, well, we've got ammonia. If we're going to make ammonia, we're going to make it from the elements in their standard states. Okay, so we've got to make 4 moles of ammonia. So you've got 2 of those, and you've got how many? You've got 6 of these, haven't you? So the stoichiometry is right. And so we're making there 4 moles of ammonia, and remember up here we just said this is the value per mole of ammonia that we're making. So we've got 4 times the enthalpy of formation for ammonia. Okay, all right. And now if we're going this way to make nitrogen monoxide or to make water, well, that is 4 times the enthalpy of formation of nitrogen dioxide. And that's actually what the question is asking us to find out. We don't know what that is. But we've also got to make water as well. So we've got to go 6 times the enthalpy of formation of water. And we've actually got that value there, haven't we? So, and we need the oxygen to do that as well. And to get the stoichiometry right, we need 5 lots of oxygen. Okay, now Hess's law is telling us that it doesn't matter which route we take, as long as the starting and end conditions are the same, we'll get the same enthalpy change. And you can see we've got a couple of routes here. We've got one route which is going that way, and another route that's going that way. So we need to start to put these 2 routes together as an equality. And so the route that's going this way is, what is it? It is 4 times the enthalpy of formation of ammonia. That's that bit there, isn't it? That's one step. The second step is the enthalpy change for the reaction, which is the enthalpy change for the reaction. I'll just call that R for the reaction. And so that route, got 2 steps, 1, 2, we've written those 2 steps there, equals the route the other way. It's a single step, isn't it, going this way? And that single step is composed of these 2 values here, which is 4 times the enthalpy of formation of nitrogen monoxide plus 6 times the enthalpy of formation of water. And you can see that we've written this out, so we've got those 1, 2 steps are the same as that 1 step over there. And so the only thing that's left then is to rearrange all these equations, or this equation, because we need to make this the subject of the equation, because that's what it's asking us to find out, the standard enthalpy change of formation of nitrogen monoxide. So let's just rearrange all of that. We're going to have 4 lots of the standard enthalpy of formation of nitrogen dioxide. That's what we're trying to find out. And to do that, we just need to subtract this term, don't we, from both sides of the equation. So we've got 4 times the enthalpy of formation of ammonia plus the enthalpy of the reaction minus 6 times the enthalpy of formation of water. So we've used Hess's law to create this equation here, And then we've just rearranged it to make the value that we want the subject to the equation. So all you have to do now is plug in the numbers. And of course, you know, in all these Hess's Law type calculations, the trick, or where you're going to get tripped up, is getting all the signs, the positives and the negatives, absolutely right. So let's just be careful about that. We've got 4 times the enthalpy of formation of ammonia, and that's 4 times minus 46. And then we've got to add the reaction enthalpy, and we're adding minus 906. You see how careful I'm being with the negative signs? And then we're taking away 6 times the standard enthalpy formation of water, and each of those is minus 242. So I've been very, very careful in this step to be very precise about the positive and the negative signs. Multiply all that up, and you get minus 184. A positive times a negative is a negative, so that becomes a negative 906. And now you've got minus 6 multiplying minus 242, so that ends up as a positive there, you see? 1452. So that's the point where you're going to go wrong with these kind of questions if you're not really, really careful. And don't try and jump from there to there. You know, use an extra 30 seconds or an extra minute to put that in to make sure you're absolutely bomb-proof and you don't get your signs wrong. Adding all that up, if you do that just in my head, I can see that overall I'm expecting that to be positive. So that's positive, actually, if I work all that out, 362 kilojoules per mole. But that's for 4 lots of the standard enthalpy of formation of nitrogen dioxide. So if you want just the enthalpy of formation, standard enthalpy of formation of nitrogen dioxide, we've got to take that figure plus 362 and divide it by 4, haven't we? And that ends up with 90.5 kilojoules per mole. We have our units in there. And you know, in these questions, whether it's negative or positive, make sure you put the sign in. You know, they're looking at it. If you check in the mark scheme, they're absolutely certain that if it's a positive value, you need to put in the positive sign there. So we've got plus 90.5 kilojoules per mole as our answer. Good. Okay, so we've left behind all the questions on ammonia and fertilizers. We're doing something completely different now, looking at the periodic table, and they've given you there, you've got period 1 up here, haven't you? Whoops. Period 1, period 2, period 3, and period 4, and then you've got your groups across the top. All right, so some of this knowledge you can probably get from GCSE work, actually. Some of it you'll have revisited or learned from new in AS level. Well, this one is an easy one to start with. An element that floats on cold water and reacts readily with it. Well, you remember experiments from GCSE. A really good example there would be sodium. Remember how that floats on the surface of the water and melts and turns into a ball. So sodium is a really good one to have in there. An element that forms an oxide that is a reducing agent. Well, you've got to think, well, what would I be thinking? I'd think, well, I know that, say, iron oxide needs to be reduced, can make iron. So if iron oxide is being reduced, then something must be being oxidized. So you could have, for example, carbon monoxide being oxidized up to carbon dioxide. So the reducing agent itself is oxidized. So you've got to think of elements that form an oxide that could itself be oxidized. Well, I've given you one here, haven't I? So carbon monoxide can be oxidized further to carbon dioxide. So carbon's a good example. Other examples you could think of, well, sulfur dioxide, that can be further oxidized, can't it, to sulfur trioxide. Or you could think of, well, I know nitrogen monoxide, we saw that earlier in the paper, that can be further oxidized to nitrogen dioxide. So these are all examples of non-metal oxides that can be further oxidized. So I think a really good choice there would be carbon. Other choices you could have will be sulfur for sulfur dioxide or nitrogen for nitrogen monoxide. I'm choosing carbon. Okay, smallest first ionization energy. Well, you need to remember, if this is the periodic table, that first ionization energies increase, don't they, as you go across a period, and they increase up a group. So you're certainly not going to be wanting to choose anything over here. So you're choosing an element which is going to be low in group 1, down here. So your choice then, if you look back, the first ionization energies are increasing this way, and they're increasing this way. So the one with the lowest first ionization energy is going to be down there. K is the symbol, the name of the element, you know, is potassium. K can go in there. Okay, so we've got to have here a giant molecular structure and an oxide that forms a simple molecular structure. Well, your only candidate there so the only candidate there is going to be carbon, isn't it? Because carbon, for its giant molecular structure, you know, is diamond. I suppose you could call use graphite as well. And the oxide, carbon monoxide or carbon dioxide, those are small molecules, aren't they? Simple molecules. So you've got the giant molecular structure and the oxide, which is a simple molecular structure. Carbon, that's a good one. Okay, period 3, you're looking for the smallest anion. Well, here's period 3. And you know, don't you, that as you go across a period, that the atomic radius is getting smaller, yeah, because you're adding electrons to the same shell, but the nuclear charge is increasing. So these atoms, their radius is getting smaller as you go across the period. But it's not asking you for an atomic radius; it's asking you for an anion, an ionic radius. Give my pen. Now, anions. I'm just fiddling around with the pen. I don't know what's happened there. Let me just go back. Turn that off, turn that on. Okay, so an anion is a negative ion. All right, so that means we're going to be looking at the ions over here, yes? Because these are all cations, aren't they? Sodium plus, magnesium 2 plus. So chloride there is chloride minus, sulfur, sulfur 2 minus, phosphorus, phosphorus 3 minus. So here you've added 1 electron, here you've added 2, which are going to repel each other, so you can think that the atom is getting larger now. Not only have you added electrons, but they're repelling each other. And this ion, this anion, is going to be even larger. You've added 3 electrons, and the anion is getting larger because of the repulsion between those electrons. So actually the smallest anion is going to be the chloride ion, Cl minus. So the element in period 3 that has the smallest anion is chlorine, because chlorine minus is smaller than sulfur 2 minus. And again, looking at period 3, we're looking for an element that forms a chloride with a low melting point. So that's going to be a simple molecular substance, isn't it? And an oxide with a high melting point. Now, a really nice candidate here is silicon dioxide as the oxide with a high melting point, and silicon tetrachloride, which is a simple molecular substance. And you just need to recall that silicon oxide, actually, that's not a very good representation of it. It forms a giant molecular substance, usually called silica, and that's found in quartz, isn't it, in rocks. So that's a really hard, high melting point substance, silicon dioxide, silica. So the good candidate here, a good example, is silicon. We can choose that as our element from period 3, which has this chloride, silicon tetrachloride, and then the oxide is a giant molecular substance, silica. Okay, we're keeping on going now. So we're looking at the elements in period 3 from sodium to argon, and something when placed in water has no reaction. Well, silicon dioxide is a really great example again, isn't it? Because silica, yeah, that's quartz. You know, that doesn't dissolve. It's a giant molecular substance. It's not going to dissolve in water. Now, an oxide that dissolves readily in water to give a strongly alkaline solution. Your clue is there. What do you know is a strong alkali? Well, we know sodium hydroxide is a strong alkali. So the oxide that's going to dissolve to give us that strong alkali is sodium oxide. If you have sodium oxide and water, what do you get? You get 2 lots of sodium hydroxide. Okay, so the oxide that dissolves easily in water to give a strongly alkaline solution, sodium oxides. 2 acidic oxides formed by the same element in group, and so this is in period 3, isn't it? So a good one to choose there. Look at period 3. Period 3, you got that's sulfur is a really good one to choose there. We talked about that earlier on anyway. 2 acidic oxides. Well, you've got sulfur dioxide, haven't you? And sulfur trioxide. That's really, really good for that. Now, the oxide that's amphoteric, remember, amphoteric is from the Greek word meaning both. That's the kind of root for that. And that means that the oxide is both acidic in its nature and basic in its nature. And the classic example of that is aluminium oxide, Al2O3. It can react with acids, acting as a base, or it can react with bases that shows acidic behavior. So it's amphoteric. It shows both acidic and basic behavior. All right. So talking about these 2 compounds here, chlorine tetrafluoride, bromine tetrafluoride, and it's given a big difference in their melting points. It's that there's similar electron configurations. We've got little dot cross diagrams for these. Sorry, just for the chlorine trifluoride. For me, the way that I do this is I say, well, chlorine, how many outer electrons does that have? Oh, it has 7 outer electrons. And for fluorine, same group actually, but there's 3 of them. 3 lots of 7 is 21. So the number of electrons is going to be, the number of valence electrons, if you like, is 28. So you've got chlorine surrounded by 3 fluorines. First of all, form the bonds. So that's chlorine there, isn't it? Okay, so at least these things are these atoms are bonded together. We're trying to make 28 valence electrons. So I'm going to put the octets for fluorine. If you count round, fluorine has 7 electrons, doesn't it? And it's sharing one of its electrons to make the bond with the chlorine atom. Give fluorine a full octet. Give fluorine a full octet. All right, so if you count around now, we've got 24 electrons used up. We've got to get rid of 28 electrons. Now, chlorine is in, if you look back, is in which period? It's in period 3, isn't it? And once you get to period 3, you can have something where these atoms can use what's called an expanded octet. They're not strictly tied to having 8 electrons. They can have an expanded octet, which is good for us because if you remember, we've got 24 electrons here. We've got to use up 28, so we can have an expanded octet for chlorine. Chlorine's now got 10 electrons around it there, can you see? So for the molecule, we've got 3 bond pairs. Can you see them? There, there, there. For fluorine, there are 3 lone pairs. There it is, there it is, there it is. And for chlorine, the central atom, there's 2 lone pairs. Added up together gives us 28 electrons in the outer shells, the valence shells of these atoms. So the 2 molecules have the same shape, chlorine trifluoride, bromine trifluoride. And you've got to suggest why the boiling points are different. Okay, so you're looking for 4 marks there. They're looking for quite a lot of suggestion there. So I'm trying to highlight the 4 anyway. So if you look at a chlorine to fluorine bond compared to a bromine to fluorine bond, the electronegativity difference is greater for bromine to fluorine than chlorine to fluorine. So that'll have a slightly more polar bond than here. So the electronegativity difference is greater for the bromine fluorine bond. That's your first point. So the electronegativity difference is greater. That's your first point. Second point, so therefore the bromine fluorine bond is more polar. There's a greater electronegativity difference. And if you've got a more polar bond, let's say that's delta negative, sorry, that's delta plus, isn't it? That's delta negative. If you've got polar bonds, then you've got a permanent dipole, and when molecules are next to each other, they'll have a intermolecular attraction between the permanent dipoles. So you've got permanent dipole, struggling with the pen, permanent dipole, intermolecular force is greater for bromine in the bromine trifluoride. And if the permanent dipole intermolecular force is greater, then, well, you've got a greater forces between the molecules, leads to a higher boiling point. Okay, we got our 4 points. Good. Okay, I think we're on to the last question now. We've done all that work on a periodic table. We're now dropping into organic chemistry, and it's giving us the 6 type of reactions that you know that you can classify your organic chemistry reactions. There they are. And you can take the substitution reactions, and you can take the addition reactions and further classify them as electrophilic, that's electron-loving, nucleophilic, that means positive charge, nucleus loving, and a free radical, if you remember, that means there's a reaction that involves an unpaired electron. You usually draw that with a single dot, don't you, to represent an unpaired reaction, an unpaired electron. So look at this one here. What type of reaction is that? Well, I mean, even if you didn't know, you could guess, couldn't you, that the bromine atom there is being replaced by this amine group. So, you know, if you didn't know, that's a replacement reaction. You could say that's a substitution. So it's pretty clear what kind of reaction that is. And to do that, you use ammonia. And ammonia has a lone pair of electrons. So that's that negative end, that negative dipole of the ammonia molecule is going to be attracted to a slight positive charge. If we drew out the mechanism for this, we'd have a slight positive charge on the carbon. And so you've got something which is looking for a positive charge. It likes positive charges. This is electrophilic. It means something that likes the positive charge of a nucleus. So the negatively charged pole of the polar molecule ammonia is going to be attracted to a slight positive charge here. So that is a kind of nucleophilic substitution. Now, actually, when you react ammonia with this halogen alkane, you end up with an ammonium salt. So if you wanted to be particularly strong on getting all your reagents in there, the first step is to use ammonia, which produces the ammonium salt, and to liberate the amine, that's the amine there, not the ammonium salt, you use sodium hydroxide. In the mark scheme, they just do that. If you had to give full reaction details, you'd say first use ammonia, then take the ammonium salt and liberate the amine by using sodium hydroxide. Okay, next one. Again, if we didn't know, we'd have to compare these two molecules. Nothing's happening at the alcohol end there. But if you look at this end, well, what's happened there? One of the hydrogens has been replaced by a bromine atom. So that's a replacement, isn't it? That's, you know, if we didn't know, that's substitution. Okay. Now, you may remember that you can take bromine, and if you use ultraviolet light, that can cause heterolytic fission of the bromine bond, giving you two bromine free radicals. That's the initiation part of a reaction. And those free radicals can go on to react further with alkanes, and you've got a kind of alkane part of the molecule over here. So we're substituting a bromine atom for a hydrogen atom. That typically happens when you've got bromine free radicals created by homolytic fission of the bromine-bromine bond. So this is free radical substitution. And actually the free radical substitution happens as part of a propagation step that follows the initiation step. So your reagent there is bromine, and to kick off the reaction, to start the initiation, you need ultraviolet light. But this step here happens during the propagation step of the free radical substitution reaction. Okay, what's happening here? You've got a propanone. This is a ketone here, isn't it? You've got that, haven't you? That's the ketone. And what's happening to it? Well, it's ending up with the, if I can get the rubber there, that's ending up with an alcohol group there and a nitrile group there. Okay, so that's not really substitution, is it? Because you've had, at the very least here, we've added a carbon atom. It's not substitution at all. So we can guess why it's not substitution. That is, we're adding something. We've added, can you see we've added a carbon here? This was initially a 3-carbon molecule. It's now a 4-carbon molecule. We've added something as addition. And the reagents that you use for that is sodium cyanide, that's Na plus Cn minus, to give you the cyanide. And you do that under acidic conditions. So it's sodium cyanide, typically in sulfuric acid. And the cyanide ion, the anion there, has got a lone pair of electrons. And so a lone pair of electrons is a bit like the lone pair of electrons up here. So that's going to be nucleophilic for the same reasons. The lone pair of electrons is attracted to an area of positive charge. Philic is Greek word for like or love. Nucleo tells us that's positive nucleus. These nucleophiles like the positive charge of a nucleus. Okay, next one. What's happening here? Well, you've got, if I draw out the molecule here, I've gone off the edge of the paper. You've got this, haven't you? You've got an alcohol. That's butan-2-ol, isn't it? And it's ending up as what? Butan-2-ene, all right? Now, you can see here that actually to get from there to there, you're removing, well, you're removing that, aren't you? And actually, if I scrub that out, you're removing one of the hydrogen atoms. You're removing that as well. So even if we didn't know, we would guess, because we're removing something, that's an elimination reaction. Elimination reactions typically remove a small molecule. In this case, the small molecule that's being removed is water. And to do that elimination, you can use a concentrated acid. You could use concentrated sulfuric acid. You could use concentrated phosphoric acid. Okay, these are the acids that you can use to do that elimination reaction. Good, keeping going with organic chemistry here. We've got an aldehyde, perhaps you're not familiar with that. And we've got some reagents. We've got to figure out how this will react, if at all. So this is going to be bromine in an addition reaction across the double bond there. So the product is going to be, and you've got to write the structural formula, is going to be CH3. And then you're going to have the bromine that's been added across the double bond, CH. Yeah, we've added bromine across the double bond, and we've added it across the double bond. Goes there, and nothing's happened to the aldehyde group. All right, so that's the product that's formed. We're just adding bromine across the double bond there. Now, phosphorus trichloride, that's typically used when you're making an acyl chloride from a carboxylic acid. And up here, we don't have a carboxylic acid at all. We've got an aldehyde. So this reagent is a kind of distractor. You know, there's no reaction going to happen there because phosphorus trichloride is typically used with carboxylic acids to make the acyl chloride. All right, hydrogen and nickel, well, it's typically used in reduction processes, hydrogenation, and you have to be careful here because typically you'd expect to do hydrogenation across the double bond. So the double bond, instead of being CH, double bond CH, is now CH2, CH2. It's a standard carbon-to-carbon single bond. But also, look very carefully because the aldehyde can also be reduced. So that there's two changes going on here. So the first change is the double bond is becoming single bonded carbon with the hydrogens there. And if you reduce the aldehyde, well, if you reduce an aldehyde, you end up with a primary alcohol. All right, so we had to catch two things there. The hydrogenation of the carbon-carbon double bond and the reduction of the aldehyde to a primary alcohol. Okay, this reagent here, sodium tetrahydroborate 3, and you use that as a reducing agent. So it's a specific reducing agent that's going to reduce the aldehyde to the primary alcohol, but won't affect the carbon-carbon double bond. So you've got this, and then you've still got the carbon-carbon double bond, haven't you? That's there. But then you've reduced the aldehyde to primary alcohol. So that's selectively reducing the aldehyde, whereas here, everything was reduced. And finally, you've got potassium dichromate. That's a well-known oxidizing agent. And you need to know that if you oxidize an aldehyde, well, if you oxidize an aldehyde, then you get carboxylic acid. So you've got, nothing's happened to the carbon-carbon double bond, but you have oxidized the aldehyde to a carboxylic acid. There it is, CO2H. Okay, now I was talking about stereoisomers here. Stereoisomer means that crotonaldehyde, its stereoisomers have the same structural formula, which was given to us further on, but it can have arrangements in space that are distinct, so different spatial arrangements. And the reason for that, of course, is that the carbon-carbon double bond fixes the groups. There's no possibility of rotation around the carbon-carbon double bond. And so the groups at either end of that carbon-carbon double bond are fixed. They can't rotate. So you end up, sorry, I've got a line down here I need to rub out. You can end up with this. Here's our carbon-carbon double bond. And we can't rotate around that. We're fixed. So we can have a methyl group up there, a hydrogen atom down here, and we can have a hydrogen atom up there, and then we can have this aldehyde group down here. Now, the other way to the other isomer is, well, you can have the methyl group up there. Here's the carbon-carbon double bond. And if the aldehyde group is up there, you can't rotate, it's fixed up there. So you've got that arrangement there. And those are distinct, they're isomers. Now, to distinguish between those isomers, you have this E or Z notation. Now, this one's the Z, and this one is the E. Now, it's a little bit tricky to remember. These come from German words. For example, Z is zusammen, which in German means together. So these are together on the same side. The most ridiculous way I heard of remembering that is very bad, kind of Jinglish, I suppose you'd call it. So the two groups are on the same side. It's a bit like if you were pretending to speak German, you say, these groups are on the same side. I'm using a Z. So these groups are on the same side, so that's going to be the Z isomer. And this is the E isomer. You just have to, well, if you've got the Z, this must be the E. It's on the opposite sides. So, and that's right. So it's asking you to label each isomer. So you've drawn them. So that must be 1 point there, 1 point there. And the labeling is giving you your third point, isn't it? Okay. So that's the Z isomer. That's the E isomer. All right. So we've been drawing these displayed formulas here. A fully displayed formula, actually, I should have done that. A fully displayed formula, whoops, what happened there? Okay, a fully displayed formula would display everything. So a fully displayed formula, instead of writing the methyl group, as I have done, CH3, fully displayed formula, to be absolutely bomb-proof on this, would be display everything. So that's the display formula. So we've had structural formulas here. They're written out like that, aren't they? We've had displayed formulas here where we're showing absolutely everything, including actually the individual hydrogen atoms around the methyl group. And now it's saying, well, okay, give us a skeletal formula. And the skeletal formula is just showing the bonds between in this case, the carbon atoms and the oxygen atom. And so the skeletal formula has all the hydrogen atoms as implicit. They're there, but we don't bother to draw them because, you know, you could see when I was drawing them on the displayed formula, it was quite labor intensive. So the skeletal formula is, there's the double bond, and that was the methyl group there. And then you've got a double bond to the oxygen. So that's our skeletal formula. We haven't drawn in all the hydrogen atoms, they're implicit, and we're just drawing in the other bonds without drawing in the hydrogen atom. We've drawn our skeletal formula. Okay, so right at the end of our work on organic chemistry here, saying, well, we had crotonaldehyde to begin with. There's the aldehyde group there. And, well, we'll draw this isomer. Remember, that's on the same side. So that's the Z isomer there. Now, when you have acidified manganate 7 and it's cold and dilute, all that means is that you're going to add across this double bond to make a diol, meaning two lots of alcohols. And so you end up with, I'm giving the displayed formula. I know it asks for the structured formula. We'll get onto that in a moment. Can you see that's become a diol? And so if we had to do the structural formula for that, well, oh, sorry, I didn't have this. I had the CH3 down here, didn't I? So the structural formula is writing it out like this. And you've now added on, those brackets there mean that this is a particular group, a functional group. And we've got another one of those, haven't we? I've got the hydrogen atom there, and be very careful here as well, because you'd think, wouldn't you, that you're done at that point, because you've added the diol across this double bond here. You think, oh, you know, I've done the question, all good. But be very careful, because you've got an aldehyde and you've got an oxidizing agent here. Well, what happens to aldehydes when they're oxidized? Well, they get changed to carboxylic acids. So actually, we've got to be very, very careful and say, well, that aldehyde is also getting oxidized up under these conditions, and so it's become a carboxylic acid. So that's a little bit tricky there, because you probably thought the game was over by the time you did your diol. You think you got that right, but you've finished too early. Be careful, because you've got to check the aldehyde as well. That's getting oxidized, isn't it? Now, you had cold, dilute conditions up here, hot, concentrated conditions down here. And you need to know that under hot, concentrated conditions, then acidified manganate 7 can split this molecule into this. You're getting 2 carbonyl compounds there. That's the one there. So there they are. So and again, we've got to be a little bit careful here, because just as we had up here, we think the whole show's over, because we've got the main thing that we think we're being tested on here, which is that the hot concentrated acidified manganate is going to split that double bond there. But just as we had here, once the thing that you're being tested on, you think, is over, you've got to remember that this is an oxidizing agent. So you could say, well, just square brackets O, that indicates oxidizing agent, that these things are going to get further oxidized, just as we had here, to carboxylic acids. So if this one is oxidized to carboxylic acid, we're going to get CH3, CO2H, ethanoic acid. And this one is going to be, that's going to be oxidized, isn't it? And that. So we're going to get a dicarboxylic acid. So we're going to get carbon joined to a carbon, and that's going to have that and that. You've got a dicarboxylic acid. So, but remember, you know, I've been looking at kind of displayed formula here. That's a structural formula. A structural formula here would be just writing out the atoms. Okay, so it seems like you've got to work pretty hard for your 3 points there. But remember that, you know, even though once you think you've got your marks, just check, because we had to check here that the aldehyde was getting oxidized up to the carboxylic acid, and here These two carbonyl compounds that were formed, both were subsequently oxidized up to the corresponding carboxylic acids. So I think we had to work quite hard there for our additional marks. Okay, that's it. We've got to the end of the paper, and we've been through all of this structured paper for AS level chemistry from summer 2013. And if you want to speak further about that or have any more questions, then follow me on the HIP chat. What am I talking about? The Slack channel. I'll be on there, and we can talk further if there's anything from that paper that you'd like to follow up on. So, see you on Slack.
This one's probably streaming as well.
So it'll be brilliant. So you just stop the broadcast, but you, oh, no, you didn't stop it, it's there.
Yeah.